time is it? Let's get light in the day here. Let's see. Come on, you go. All righty. So let's take a look at 22.10b. So let's see. We've got the aromatic ring here. If we wanted to use cyanide, well, that would take care of these two atoms, the carbon and the nitrogen. And of course, we would reduce it to the primary amine. So that would mean that we would need the aromatic ring with a methylene. So let's see here. What we would do is we would use benzyl bromide, which is this compound. Comes up all the time in organic chemistry. We treat that with sodium cyanide, and that would give us the nitrile. This, oops, there we go. So there's the nitrile. Then we're going to reduce that with lithium aluminum hydride followed by water. And that is going to give us the desired primary amine. So 1, 2 carbons. And there's our primary amine. And then if we wanted to use or go through a carboxylic acid, we would, of course, have the carbonyl here to make the primary amine. And so our carboxylic acid would look like this. So we'd have 1, 2 carbons there, and we'd start with this carboxylic acid. So same thing as before. First step would be thionyl chloride to make the acid chloride, then excess ammonia to make the primary amide. Let's pencil the primary amide in here. Oops. There we go. That's better. Primary amide, and then just lithium aluminum hydride followed by treatment with water, and that's going to give us product. So and there you have it, folks. So we made some primary amines either by using an SN2 followed by reduction, or by making an acid chloride, then a primary amide, and then reducing that. All right, let's move on to section 22.5, which deals with the preparation of amines via substitution. And check this out. It says if you take a compound like ammonia and treat it with methyl iodide, that an amine is such a great nucleophile that it's going to undergo a substitution, just an SN2, to give you an alkyl ammonium ion. And then you can deprotonate that to make a primary amine. And it says this is an efficient way to make a quaternary ammonium salt. So this here is a quaternary ammonium salt. Sometimes we call them quats. Sometimes, not kidding, the quat. Anyhow, what's interesting about this though is that once you make the primary amine, it's like the Energizer Bunny. It keeps going and going and going, and you can end up alkylating over and over. So once you make that primary amine, it can do another SN2 to make a secondary amine. Then it can undergo another SN2 to make a tertiary amine, and you get the idea. And then you end up with your quat, your quaternary ammonium salt. So monoalkylation, like trying to stop here, is actually really difficult because it just keeps getting better and better as a nucleophile, because as it picks up alkyl groups, well, they're electron donating, so it makes the base even stronger. So it's an even better nucleophile. So you might be wondering, well, how do I stop, or how do I just effectively perform a monoalkylation? That would be a great question. One alternative we have to make a primary amine is to use what's called the azide synthesis. In order to do the azide synthesis, we need to have some kind of alkyl halide. So we have an alkyl halide, and we can do an SN2 with this compound here, and this is called sodium azide. If you're wondering about the Lewis structure of azide, I have it on the slide coming up. So sodium azide, and azide is obviously a good nucleophile, so we could just draw N3- like this, and it can do an SN2 like that. And then once you have the azide, so this is a new functional group, you can reduce that using hydrogenation conditions or reduction conditions. And this is a better way to make a primary amine than trying to alkylate or monoalkylate ammonia, because we saw that exhaustive alkylation right here. Sometimes we call this, I'll just pencil it in since I didn't do it before, sometimes we call this exhaustive alkylation, where it just keeps alkylating and alkylating and alkylating. Now you might be wondering, is there any utility to exhaustive alkylation? And the answer is yes, there is, in something called Hofmann elimination. That's something we'll discuss the next class, so don't worry about it for today. Let's go back here. Just another quick thing I'll say about the azides is that, and I don't have a lot of experience with azides, is that azides are explosive. So, not every azide is the safest thing to work with. And again, I'm not an azide expert, but I have seen people work with them, and I do know that they are explosive. So let's take a look at this mechanism and the reduction a little bit. So if you go and look at the azide, this is the Lewis structure of the azide ion right here. This is your azide ion. And this is our SN2 reaction. So we have the loss of the halogen as the leaving group, and then the lithium aluminum hydride can deliver a hydride to add this hydrogen right here. And then you can see that it undergoes the expulsion of nitrogen gas as a leaving group. So you lose that nitrogen gas, and then you end up with an amide ion, which can be protonated by water. So you have your lithium aluminum hydride followed by water. So essentially, this is the first step, adding the sodium azide. This is the second step, the lithium aluminum hydride. And then this would be the third step, the protonation, the adding of water. So that's a better way to make a primary amine. However, we have other ways to make amines. Another way to make an amine is to use what's called the Gabriel synthesis. And this is a way to make primary or secondary amines from a molecule called phthalamide. So you need to know this molecule here, phthalamide. And the first thing you need to do is convert phthalamide into potassium phthalamide. And the way that we do that is just by treating it with potassium hydroxide. Phthalamide, this proton has a pKa of around 8.3-ish, and then water has a pKa, of course, of around 15.7, so the equilibrium is definitely going to lie to the side of the water. So we get phthalamide, and then we can make potassium phthalamide. Well, you can imagine that potassium phthalamide, since we have a negative charge here on this nitrogen, it makes a dandy nucleophile. And so what we can do is we can take an alkyl halide, either a methyl or a primary or even a secondary alkyl halide, and we can react it with the potassium phthalamide to make this intermediate. All right, well then what do we do with that intermediate? Well, you've got a couple of options. Options are to either take the alkylated phthalamide and to treat it with aqueous acid. That gives you this compound here. This is called phthalic acid. So the phthalic acid and the ammonium ion. But of course, you have to take that and you've got to treat that with sodium hydroxide, so NaOH, to make the amine. Or alternatively, you can use hydrazine. So this is, again, we've seen this molecule before, but this is called hydrazine. And I don't think that this works as well. I'm not sure which one of these is a better method to make the amine, but I know that this one is only one step and this one is two steps. So based on my experience teaching this class over the years, my students tend to prefer this method because they just have to remember one step. You just treat it with hydrazine and you end up with the uncharged amine. And I don't blame them for wanting to, use the simplest way of doing it. So the next question that I want to look at deals with Gabriel synthesis. How would you use Gabriel synthesis to make each of these compounds? So remember, the nitrogen in the amine is the part that's going to come from the phthalamide. So if we draw the whole gaudy structure, the phthalamide, and I'm just going to draw the phthalamide ion, so the potassium phthalamide. This nitrogen, I'll highlight it in yellow, this comes from here. The entire remainder of the molecule, all of this comes from the alkyl halide, which is going to be this alkyl bromide, iodide, or chloride. Okay, so everything comes from here. Now, you could either start with like this, but if you want to show every single step, what you could do is this. I'll just show you quickly. You could write out the whole phthalamide compound, okay? And you could say, okay, well, step one, I'm going to treat it with potassium hydroxide. That's going to make potassium phthalamide. In the second step, I'm going to treat it with the alkyl halide. pencil in the alkyl halide. And then in the third step, I'm going to treat it with hydrazine. Let's draw the intermediate. You know what? Let's do it just for fun. So you're going to end up with this intermediate, which looks like this. And I don't even know if our book draws out all these intermediates. I doubt it. So there we go, like this. And then in the last step, you're going to treat it with hydrazine. And again, you could do the two-step process. That works too. You could treat it with aqueous acid followed by aqueous base. That works too. But I think that this is kind of a faster way of doing it. So you're going to end up with the desired product. So you end up with your primary amine. And then if you go back here, I don't think I'm going to ask you to draw this side product. I wouldn't really worry about it a whole lot. But you could pencil that in if you wanted to, but that's not what they're asking us to make. They just want us to make this compound. Nothing more than that. All right? Now I'm going to erase some of these details here just to kind of clean up the slide a little bit. So just bear with me. You can take a look at the second problem. We're going to tackle it in just a second here. We make some room. You're an organic chemist. You take up lots of space solving all your practice problems. So for the next one, the same rationale applies. This nitrogen is going to come from the phthalamide. And now we're going to have all of this coming from our alkyl halide. So we're going to use the exact same approach. We're going to start with phthalamide. So here's our phthalamide. Let's draw the whole thing out here. Oops. There we go. First step, potassium hydroxide to make the potassium phthalamide. The second step, we're going to use this whole gaudy thing here. So I have both of these aromatic rings tied together like this. And then we're going to have the bromine here. So it's a secondary alkyl halide, and we're going to get some SN2 product. And then, of course, in the last step, you would treat that, step 3, you would treat that with hydrazine, and that's going to give you the final product. I'll just write the word product in here. And of course, you also end up with this compound, but again, that's not what they're asking us to make. So let's not worry about the side product right now. It's getting pretty late in the day. I'm a little tired, but let's cover one more quick section here. We get more than enough time to cover all the remainder of the material in our next class. But I wanted to take a look at just an introduction to reductive amination with you. The reason why is this reaction is so near and dear to my heart. I think that most of you are fully aware that I worked as a chemist most of my adult life. I've only taught for a few years. Well, actually, it's a long time now, but I worked for 15 years in big pharma. And out of all the reactions I did, which is thousands and thousands and thousands of them, I think that one that I might have done the most, maybe, it could be reductive amination. Okay, I did thousands of reductive aminations, and the reason why, it's a very effective and rapid way of making amines. And as you saw, amines are just almost ubiquitous in drugs. Like they're everywhere in drugs. So we were trying to develop new medicines, and so we'd be making amines all the time. I needed a fast way to do it, and reductive amination is a great way to do it. And the good news is that you already understand a lot of the chemistry because it involves amines. So if we take a ketone, we know that we can treat it with a catalytic amount of acid. Ammonia, of course, you end up losing water in the process, and we can make an imine. And then we can reduce that amine using hydrogenation. Sure, that works, to make an amine. But if we do this step, so if we were to do the first step only, I'm just going to delete this. If we were to just do this step, and if we could find another reagent that we could put in here that could reduce this in situ, and in situ is just Latin for in place, meaning in the same reaction flask, then we can like kind of kill two birds with one stone. You see what I mean? Like we'd be able to do all of this, go from here to here in one step. So in situ, again, means in place or in the same flask. So there is a bunch of reagents that can be used to do reductive amination. Let me just get that out there. There's a whole holy host of them. You don't need to know everything out there. There's only one, the most important one, most commonly used one is sodium cyanoborohydride. Everybody who's hearing the sound of my voice remembers NaBH4. Okay, we use that all the way since chapter 12 in this class. Sodium cyanoborohydride for this and that. So sodium cyanoborohydride is such a strong reducing agent. It's weaker than lithium aluminum hydride, but it's strong enough that if you were to put it in a flask with a ketone, it's going to reduce it to an alcohol. So you can't put that in your flask. However, when you add a cyano group, the cyano group is electron withdrawing, and it stabilizes the negative charge on the bromine. And the bottom line is that this is a weaker reducing agent than sodium borohydride. So it doesn't react with the ketone or aldehyde. It doesn't react until the imine is formed. So again, once the imine is formed, the sodium cyanoborohydride just delivers the hydride to it, and it reduces it to the amine directly. This is one of the coolest reactions I can think of, because it's all in one pot. It's all in one flask. You take your ketone, you combine it with your amine, a little bit of acid, and your sodium cyanoborohydride, which is just a white solid powder. You mass it out, and then you let it stir for a few hours, and it's like magic. You make that primary amine if you have ammonia. If you use a primary amine, you make a secondary amine, and if you use a secondary amine, you get a tertiary amine. Very, very interesting chemistry, very quick chemistry. And again, the whole idea of the sodium cyanoborohydride is that the cyano group, this group here, is electron withdrawing, which stabilizes the negative charge on the boron and renders it essentially more selective. That's the whole rationale behind using sodium cyanoborohydride. So this is what we call reductive amination, because you're forming an amine. It's being reduced to produce an amine. Let's just take a look at a practice problem. Let's take a look at a question and see if we can find a way to do a reductive amination. And then I think we'll call it a day for today, because after this, we've only got a couple of sections left. So we've got to check here. There we go. So let's say you wanted to make 22.14 and you wanted to make this compound via reductive amination. Well, there's a couple of ways you could do it. You could imagine, you could imagine breaking this bond here, okay? Or you could imagine breaking this bond here. You could imagine putting the methyl group on or the propyl group on. Let's start with the propyl group. We'll make it interesting. If you wanted to put the propyl group on, what would you do? So maybe I'll delete this, okay? If you wanted to add that propyl group, you would have the amine, and then the ketone, the aldehyde that you would have would be, where's my pen? It would be this aldehyde, propionaldehyde, and then you would have this amine. So let's draw that out here. So your amine, and I mean, you could put these in any order you want, technically. But why don't we just start by drawing propionaldehyde, and then we'll write the amine. So it's methylpropylamine. So let's just pencil that in here like this. 1, 2, 3. Catalytic amount of acid. And then we'll put in our sodium cyanoborohydride. Sodium cyanoborohydride. So we write NaBH3CN like this, and that's going to give us the product in in B. If we wanted to break off, this bond here, then our carbonyl would just have one carbon. So it would just be formaldehyde in that case. So that means we would start out with dipropylamine like this, and we would treat it with formaldehyde, catalytic amount of acid, and sodium cyanoborohydride. And again, you can put the aldehyde first or the amine first. It doesn't matter. You're mixing them all together anyway, and that would give you the product. So what I want you to do before class on Wednesday is I'd like you to, at a minimum, give this one a try, and hopefully this one a try as well. And we'll come back and we'll take a look at those questions. And also, I want you to take a look at this one here, which is the methamphetamine synthesis, okay? So this is the whole synthesis of crystal meth, and maybe I'll talk about a little bit more about ephedrine and pseudoephedrine that class today. I started to, but I stopped myself because I didn't want to take up too much class time on that. But let's just review a little bit of what we've covered already. We looked at 3 different ways to make a primary amine. We looked at the Gabriel synthesis using potassium phthalamide, which is of course made from phthalamide and treating it with potassium hydroxide. Then we looked at the azide synthesis using sodium azide and then reducing that. And you could use hydrogenation. That's all they have listed here. Or we'll pencil it in here. Or you could use, we'll put here 2 LAH followed by 3 water. Either one of those works. And then one of my favorites is reductive amination, a really cool way of making an amine. So we looked at all of these as opportunities for making primary amines. And if we want to make a secondary or tertiary amine, we saw that the best way to do that is to use reductive amination. Right? We can always use reductive amination to make secondary and tertiary amines. And then if you want to make a quaternary ammonium ions or quat, to do that, you would just alkylate a tertiary amine, using an SN2 reaction. So now you know how to make primary, secondary, tertiary amines, and even a quaternary ammonium ion. So we've got all kinds of new strategies for making amines.